Good morning, most awesome chemical engineering students. Today I have a treat for you. I'm going to show you how to model, using the brute force method, a two-stage distillation column, but the chemicals involved, ethanol and water, are a non-ideal system, and so we'll have to model the VLE behavior with a polynomial fit. Let's go. Here is the problem statement. 100 moles per second of a 20 mole percent ethanol and 80 mole percent water mixture is fed to the bottom stage of a two-stage distillation column. Stage 1, that's the top stage, acts as a partial condenser, and stage 2 acts as a partial reboiler. 40 moles per second of vapor leaves stage 1, and the reflux ratio is 1. Determine all unknown temperatures, compositions, and flow rates. We'll start the solution with a process flow diagram and then conduct a degree of freedom analysis. The two boxes here represent the two stages of the distillation column. This is a partial condenser and this is a partial reboiler. We're feeding to the second stage, the bottom stage, and we're taking out of the top stage a vapor, and the ratio of the liquid leaving that stage to the vapor leaving that stage is the reflux ratio. A liquid product is taken from the second stage. All these streams entering and leaving these stages are labeled. So we have the vapor leaving stage 1 and the liquid leaving stage 1, the vapor leaving stage 2 and the liquid leaving stage 2, and the feed. In addition to this, we have temperatures associated with both stages. Now, the yellow boxes represent specifications in the problem statement. So we know this vapor flow rate, and we know the feed and its composition. In the blue boxes, though, those are values that we don't know and we'll be figuring out. So for a DOF analysis, we'll need to make a list of the unknowns. And they will be starting, I guess, at the top, Y2, T1, V2, Y2, L1, X1, T2, L1, and X1. Wow. 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns. So I'll write that here. 9 unknowns. That means we need 9 equations in order to solve this system. Remember, we're going to be using the brute force method, which means we're going to solve all 9 equations for all 9 variables simultaneously. So for the equations, hopefully we have 9 equations. We have, for each stage, we have 2 mole balances, and we have 2 equilibrium relationships. 1 for ethanol, 1 for water. That's 8. Oh, but we also have a process specification. And that's the reflux ratio. So it does look like we have 9 equations to solve for these 9 unknowns. I hope you watched my tutorial fitting VLE data with polynomial functions. I got the VLE data from the process simulator ChemCAD using the Wilson activity coefficient model. It is the blue line here on this XY diagram. Now we can fit that with a polynomial equation, but even the 6th order polynomial, which is the most Excel will do, does a pretty good job, and you could use this, but it's not exactly right. You can see it's a little bit overshoots the curve here, maybe undershoots it a little bit here. Not too bad, but we can do better, and I'll show you in a minute. For the TXY diagram, we have a similar situation. We can fit the dew point and bubble point curves with a 6th order polynomial, but it's okay, probably will work, okay, but it doesn't quite match the data. You see here. We can do better than that, and I'll show you how. Here I've broken up the XY plot into 2 places that seem to me should fit better to a polynomial. One is from 0 to 0.1, and then from 0.1 to 0.8. Beyond that, we get pretty close to the azeotropic composition, and we're not going to go any further than that, so I just cut off the plot at 0.8. Now, this is much more of a smooth line, and this is a smooth curve also. And sure enough, if we fit this part of the curve to a 4th order polynomial, we get almost a perfect fit. And this part of the curve, we had to use a 6th order polynomial, but again, it's pretty much a perfect fit. So by splitting this up and having 2 equations, depending on whether you're below or above x equals 0.1, we get a much better fit of the data. I did the same thing here with the TXY data. I noted that the dew point curve was pretty smooth up until this point here, about 0.5, and so that I fit with the 3rd order polynomial. And then from here to 0.8, I fit that with a 4th order polynomial. Both are pretty much perfect fits. For the bubble point curve, I split it right here at 0.15 and fit this portion of the curve with a 4th order polynomial, and this part of the curve with, let's see, a 5th order polynomial. Again, pretty much perfect fits. By the way, this TXY diagram should be X and Y. This is for the Y values, this is for the X values. Now we have, in the previous slide, XY equilibrium data. And on this one, we've got the bubble point curve and the dew point curve. We only need 2 equilibrium relationships to solve this problem. So I'm going to use just the equations on this graph for the bubble point and the dew point. Here is my simulation, and I will go over this a little bit. Up here, I have all those constants for the bubble point and dew point curves. So t equals f of y, that's the dew point curve. Temperature is a function of x, that's the bubble point curve. And the ranges that I split them up into. And here are the constants for those polynomial equations. This one here, for instance, the dew point curve in the lower portion, it has just a 3rd order polynomial, so there are no constants here. Now I've entered the specifications in the problem statement for feed and vapor flow rate. I put in guesses here for the compositions and flow rates and temperatures. Those are just wild guesses, kind of wild. And over here I have the equations in green for both stages. So we have the total mole balance, the ethanol mole balance, the bubble point equation and dew point equation, which I'll discuss in a second. And here is the process specification, which basically in this cell, we just have V minus L. They should be equal since it's a reflux ratio of 1. And so my guess didn't have that, so that's not 0. We also have the mole balances and equilibrium relationships for the second stage here. Over here, I've calculated a bubble point or dew point function based on, for the dew point, this composition, for the bubble point, this composition. It looks like this. The temperature is a function for, say, the bubble point, a function of x, right, that polynomial function, and then I subtract from that the temperature of the stage. That's this temperature here. If we have the proper value for x in that cell here, then this should be 0. But it's not. Here for the 0 to 0.15 range, and here for the 0.15 to 0.8 range. They're not, because we don't have the correct composition here for this temperature. But we'll be changing that. For the dew points, it'll be exactly the same thing. We'll have a function of y minus the temperature. And does that equal 0? Over here, I just have a logical statement that says, for the bubble point, if x is less than or equal to 0.15, then put into this cell this value. If it's not less than or equal to 0.15, then put in this value. So, and we do this similar type of thing with the dew point. Let me show you how that looks. I've marked the cell numbers of specific values from the ethanol water EW tutorial spreadsheet, Excel spreadsheet, which, by the way, is posted, and you should actually download it and follow along with it as you go through this tutorial. But that way I can reference these cells as I show you this logic statement. The statement right here in this cell will be if, so it's a logical statement, see, if cell H15 is less than or equal to 0.15, then, which is just a comma, cell N11. Otherwise, comma, P11. And then close the parentheses. So, again, if the value in H15, which is the X value, that's an equilibrium value coming out of stage 1, if that is less than this value, 0.15, then use this equation, which would be this one right here, and that's the value here calculated. If not, if it's greater than 0.15, then use this value. So now we have 9 equations here and here and 9 unknowns. And so we can set up Solver to determine what these flow rates, temperatures, and compositions are. Okay, here I pressed Solver and solve, and it came up with the answers. And so we have increase in ethanol composition with this two-stage process from 0.2 to 0.4, and a decrease in the bottoms product from 0.2 to 0.04, taking out 60 moles of bottom product and 40 moles of top product. All these equations have been satisfied. So if we look over here, the x value here is 0.1, so it calculated the bubble point using this equation, not this one here. And you can tell it's 0, and that's not 0. It looks like all of these compositions, both liquid phase and vapor phase, use the lower range compositions formulas. Here on this XY diagram, I have plotted the leaving compositions, which are in equilibrium, so no surprise that they are on the equilibrium line. And this is the passing stream composition between stages 1 and 2. Just for fun, the top stream, V1, does not have a passing stream, so I plotted it just on the diagonal here. So 0.44, 0.44, and the bottom liquid stream also has no passing stream, and so I just plotted it here on the diagonal. The reason will be clear on the next slide. Okay, so here I've connected that top stream to the stream compositions leaving that first stage, to the passing stream compositions, to the streams leaving stage 2, and then connecting that to the liquid stream leaving stage 2. And you can see the beginnings of a stair-step construction, which will be developed in later chapters into what's called the McCabe-Thiele method. But that's just kind of interesting at this point.